Hello everyone. So I'm Amila Jayasinghe. I'm from Structures Research Group here, and I am researching on how to reduce carbon footprint from buildings. And in today's presentation, I will be talking about optimization of flat slabs around one of my projects in my PhD. So now we all talk about climate change, and this is to do with the carbon emissions because of the human activities. As a structural engineer here, I am trying to save the world basically because with cement production alone, it emits 6% of total carbon emissions due to human activities. And on top of that, we have steel production for constructions and construction machine-related emissions and disposal-related emissions. So it's a lot of carbon. So this is the British European standard for assessing environmental performance of buildings. And as an example, if we take this building, so starting from the material extractions for these bricks, we have emitted carbon to the atmosphere. So from the product stage, and then we have to produce the construction materials, then we have to construct the building, and then we are using the building with all the lights and heat and everything, and we are going on with the life cycle of the building. So, but if we talk about the use stage of the building, we are getting better at this throughout the time. We are talking about the decarbonization of grid. We are talking about energy efficient appliances. So as a result, now this part has become more predominant. This is becoming predominant because with the proper understanding of the use stage, we have to talk about the material optimization stage as a civil engineers. So let's talk about how we design buildings so that we can have some insight about what we can do. So first we have the architectural design depending on the client's requirements and the purpose. And then we have to design the structural layout of the building to understand what kind of structural materials we are using, what kind of structural column layout we have, what kind of floor designs we have. And then we have to do the detailed structural design in terms of reinforcement design. And in structural design, we have to often talk about two considerations. So the first one is ultimate limit state, that is to do with the safety, it is to do with the stability and collapse. So the other one is the serviceability limit state, that is to do with the comfortableness, and it is more often to do with deformation and vibration. So in a conventional design process, we can tackle this using span to depth ratios. As an example, if we can size the structural members within these conventional rules, we can often satisfy the serviceability criterion, but we have to then design the reinforcement according to that. But the problem with this is, if we can increase the depth of the member, we can reduce the amount of reinforcement we need. Vice versa, if we can reduce the depth of the member, we have to increase the reinforcement we need. But so that means if we can get around this table in some other means, we can have range of designs designed for a specific purpose. So the problem here is different materials have different amount of embodied carbon. So this means 1 kilogram of steel in terms of production has already emitted 1.2 kilograms of embodied carbon emissions to the atmosphere. So if we can have a range of designs for the same purpose, that means we can have a range of designs with different amount of steel and concrete. That means we can have different amount of embodied carbon for the same purpose. So this is my research plan for this purpose. I am looking at this kind of floor design for an office building, changing concrete grade of the slab thickness, and column spacing and column sizes. So since I'm essentially deviating from the conventional practices, I have to model for long-term nonlinear deformation of the structure separately. So this is the model I created for the structural deformation estimations. I have to couple the optimization algorithm with these kind of analysis so that we can assess the deformation in a much computational way rather than having a simplified way which is inherently carbon intensive. So results came out a bit interesting, And these two cases have been designed with two different column grades for the same structural load. So if we have the column spacing of 7 meter by 7 meter column grade, the design is often not governed by deflection criteria, but if we use 9 meter by 9 meter column grade, so we cannot go to the minimum possible because deflection is limiting our potential. Always the optimization algorithm suggested to minimize slab thickness, but then we have some other consideration to take into account. So expanding the previous graph for different column sizes, depending on the 3 column sizes, the failure criteria has been different. But the main part I want you to look at is, so this line blocks the because of the deflection criterion, but if we can get around with that, we can reduce up to this much of embodied carbon. And if we play around with the grade of concrete next, even if we have to have thicker members with low strength concrete, that would be better in terms of embodied carbon rather than going for high strength concrete. So this is the overview of the optimization algorithm I got. So with the column space, for different column spacings, this is the optimum slab depths I can have. So this dashed black line is the one from the conventional span to depth ratio. So as you can see, there's this much of embodied carbon we can be saved if we can get around with the conventional design approaches. But the problem is we have to think about the deflection as well. So this dashed line represents the conventional design. And if we reduce the slab depth, this deflection will go above our required standard values. But there again, these standard values may be subjective depending on different codes we consider. So we can play around with it if it is worth it. But the problem was it was not so worth it. So we can allow for more deflection, but that means the potential savings of embodied carbon because of that compromise is not that worth it. But still, these boxes represent the conventional design from the span to depth ratios, but we could still save up to this amount of around like 10% of embodied carbon if we do the parametric analysis deviating from the conventional design process, but to carefully consider the deflection as well. So this is something to do with the increasing reinforcement. So even if after designing everything to the minimum possible slab depth, we can still further reduce the slab depth by increasing the amount of reinforcement. So some people say this can be a little bit less costly, but in terms of embodied carbon, it turned out to be, it is also not one of the very effective methods to reduce embodied carbon overall. So, however, we have a problem with the concept of embodied carbon, because when we say for 1 kilogram of steel, we have emitted 1.2 kilograms of carbon dioxide in the atmosphere, that is not a very finite specific value. Depending on the method of construction, in the geography of location, there can be inherent variations and some sort of uncertainty is also there. So these graphs talk about the sensitivity of the entire analysis, but it turned out to be not so sensitive in terms of minimizing slab thickness. This says even if we have carbon of steel more than 200% of the current values, it would still make sure the optimum design should be with the minimum possible thickness. So, but for the increasing amount of reinforcement to satisfy reflection, there can be a chances where we can do this effectively if we have maybe only 20% less embodied carbon steel with us. So this is the overall potential we can go. So all these designs have the same structural performance, but compared to the minimum embodied carbon design we can have, it can go up to 120% from that point. So it is really important to focus on design of slabs at the very initial design stages. So thank you very much for your interest, and I'm happy to take your questions.
Thank you very much. We hope you saved the word. Is there any question? Yes, coming.
So all of this is like parameter research in finite element analysis, but how much do you trust the outputs of these finite element models? Like, are they trustworthy? Like, because you're optimizing for what the computer says is the best, but how much, like, is it actually a good representation of reality?
Well, so I guess you are talking about the finite element analysis, not the overall approach, right?
Yeah, like how much do we trust the results of the finite element analysis?
I think it would depend on the case. So they say no matter what kind of sophisticated model we use for finite element analysis, the results would be varied within, I think, plus 15% to minus 30%. So in this kind of analysis, this is often to say about what kind of variation we can expect rather than this is the exact amount. Anyway, what is the purpose of saying the deflection is exactly this amount of millimeters? Would you really care if it is like 2 millimeters more in this lab? I don't think so. That is one of the purposes in this research, to discuss this kind of serviceability criteria in a more broader manner rather than sticking to the limits like the deflection has to be span over 250. I was trying to push that limit if it is worth it. So to some level it is worth it, but maybe not to the extremes. So we can trust the finite element approach to some extent, but we have to know what that means and what kind of variations it can have. Okay.
Thank you. Yes, coming.
Have you assessed the spacing of the columns in the buttery in relation to the slab of the hall above?
No. So in terms of butter, if I'm really speaking about that, I think it has something to do with mainly the architecture design. So out of my scope in this today's presentation, so in the building construction, sometimes it can often be governed by the architectural design, but at the same time there will be some push as a structural engineer who cares about the environment to maybe reduce the column spacing, but not necessarily. As you can see, even in this graph, it doesn't necessarily mean you have to minimize the column spacing, but the variation is not linear as well. So just like that, I think in the battery, I don't think you can have a column in the middle of that. Maybe it's well designed in that sense, but in an overall approach, we have to understand that we can negotiate between the structural design and the architectural design, and it has to be done in a much qualitative manner rather than saying this should be the case.
Thank you so much. I'm looking for a very quick question if someone has it. Yes?
How does the cost of materials and variability play into sort of perhaps incentivizing improved or better lower carbon emissions?
That is a good question that is often discussed in very detailed manner. In terms of material consumption, most probably they would go hand in hand, but the cost savings sometimes can be coming from other considerations. As an example, if I'm trying to design a beam, maybe sticking much reinforcement so that it can easy to bind can be cost effective, but it can be carbon high because of the higher material usage. So those kind of considerations can be a case where we have discrepancies between the carbon considerations and the cost considerations, but usually in most of the cases in terms of material consumptions, they go hand in hand.
Thank you so much. With this, the time is up.